All right, today's lecture is a technique used to determine the concentration of an unknown substance, and the technique is called titration. Titration is where we add one reactant to another very slowly using a piece of glassware called a burette. And by doing that, we're able to figure out what amount of one chemical is needed to reach the point of equivalency. And the point of equivalency is where the mole quantities of both reactants are equal. And therefore, what will happen in a lot of points is that you're going to set up the experiment so that there's a color change or some other type of physical observation that occurs that lets you know when this point occurs. Now, I'm going to show you real quickly. I'm going to turn the page. Okay, so let's do one more example. But now instead of doing an acid-base reaction, let's do a titration, which there's a redox reaction. And here's a great real-life example scenario where we're looking at blood alcohol levels. So if someone's being pulled over and they have to take a blood sample to be able to test for what their blood alcohol count is versus using a breathalyzer, which has a lot more randomness to it. It's not quite as bulletproof when it comes to quartz. So what we do in this situation is to take a sample of blood and then analyze it to see what the blood alcohol count of the individual is. To do that, the ethanol, which is what comes from the alcohol beverages, is titrated against dichromate to produce carbon dioxide and the chromium ion. They tell us it's a redox reaction, so it's a good review of how to balance redox. So the first step is to separate the reaction into the two half reactions. And I'm going to give a lot of room so I can come back and come through. Again, the way we can split them is by identifying unique elements, in this case chromium, and you put chromium with chromium to split the reaction to two half reactions. Okay, step one, balance the elements other than hydrogen and oxygen first. We have 2 carbons on the left, so I need to put 2 carbons on the right. Next, we balance oxygen by adding water. Well, I have 4 oxygens on the right side, 2 times 2, but I only have 1 oxygen on the left, so I need to add 3 more water molecules. That gives me 6 hydrogens in the ethanol and 6 with the hydrogen in the water, so that tells me I've got to add 12 hydrogen ions to balance. Now the carbons, the hydrogens, and the oxygens are all balanced. The last step is electrons. There is 0 charge on the ethanol, 0 charge on the water, 0 charge on the carbon dioxide, but there's a plus 12 with the 12 hydrogen ions. So the more positive side we add electrons to, and I have to make the positive 12 become 0 to match the left side. So therefore I need 12 electrons. That is a balanced half reaction. Since the electrons are on the product side, this would be the oxidation half reaction. This is an oxidation reaction because the electrons are on the product side. The ethanol, the C2H5OH, is losing 12 electrons per balanced equation, and when substances lose electrons, that is oxidizing. So the ethanol is being oxidized in this redox reaction. Okay, next reaction, there's 2 chromiums. I need to put 2 chromiums on the right. There are 7 oxygens with the dichromate, so I need to add 7 water to balance the oxygens. I then have to come back and add 14 hydrogen ions. Okay, because 7 times 2 is 14 hydrogen ions. Now, the dichromate has got a charge of -2. The 14 hydrogens is plus 14. That adds up to a total of plus 12. On the right side, we have 2 times plus 3 is plus 6, and the oxygen is 0, so it's plus 6. So we have plus 12 and plus 6. So I have to make the more positive side into the more negative side. So how do I make plus 12 become plus 6? I need to add 6 electrons. And we see now electrons are on both on the reactant side and the product side, which they need to, which tells me the second reaction is the reduction half reaction. You can't have both half reactions be reduction or oxidation. One has to be one has to be the other. The next step, to balance this reaction, we have to make sure that the number of electrons in both reactions is the same. So now I got to come by and I have to double the dichromate reaction. Okay, so that gives me 2 dichromates, 28 hydrogens, 12 electrons, 4 chromiums, and 14 waters. Now I'm going to use a different color here to hopefully make this a little bit easier to see. So now I simply need to summate the overall equation. Okay, so you'll notice that when we tend to do these reactions, we tend to get water on both sides of the reaction. When we can do this, we should reduce. So there's 3 waters on the left and there's 14 on the right. So the side of less water we cross off, and this reduces this down to 11 waters on the right side. There are 28 hydrogens on the left and there's 12 hydrogens on the right. So again, the less side will cancel and will subtract, and now my 28 gets reduced down to 16. And then since there's 12 electrons on both sides, they will cancel. Remember, when we are done, the overall equation should no longer have electrons in the reaction. What I'm left with is the answer. So ethanol plus 2 dichromates plus 16 hydrogen ions produces 2 carbon dioxide, 4 chromiums, and 11 waters. Now we should check to make sure that that reaction is balanced. So I got 2 carbons on the left, 2 on the right, 6 hydrogens and 16 more is 22 hydrogens on the left. 11 times 2 is 22. 2 chromiums. Oh, excuse me, 2. That should have been dichromate. Cr2O7, my fault, I'm sorry, I forgot the 2 there with the dichromate. 2 times 2 is 4, and there's 4 chromiums. Good catch there, and that's why we always check the problems. And lastly, the oxygens. There's 1 oxygen with the ethanol, and then there's 2 times 7, which is 14. 14 plus 1 more is 15 oxygens. 2 times 2 is 4, and 11 times 1 is 11, so 11 plus 4 is 15. So we have 15 oxygens on each side. The last thing you should check is charge. There's 0 with the ethanol. There's -4 with the dichromate. There's 16 pluses with the hydrogen. So that leaves me with a +12. On the right side, there's 0 with the carbon dioxide, 0 with the water. 4 times 3 is +12 on the left. So we have +12 on both sides. The reaction is balanced. So our reaction is 1 ethanol, 2 dichromates, 16 hydrogen ions, produces 2 carbon dioxides, 4 chromiums, and 11 waters. Okay, the tough part is done. So now the next step is to figure out the concentration of the ethanol in this person's bloodstream. To do that, we follow the same 3 steps as we did in the previous problem. Step 1, I know the volume and the molarity of the dichromate, which is the titrant. So I multiply the molarity by the volume of it in liters. 10 milliliters is 0.01 liters. We multiply, and that gives me the moles of the dichromate. Step 2, once I know the moles of the one reactant, I figure out the moles of the other reactant using the mole ratio. And looking at the balanced equation, for every 2 moles of dichromate ion, there is 1 mole of ethanol. 0.0005 moles of ethanol. Dividing that by the fact that the sample to be titrated was 20 milliliters. That's how much blood plasma was titrated. So if we divide that by the volume of the sample in liters, Moles divided by liters will give me my molarity. So 0.0005 divided by 0.02 gives me a molarity of 0.025 capital M. So we would say that in the blood plasma, there is a concentration of 0.025 molar ethanol. Currently, 10% blood alcohol, or 0.01. I think the current blood alcohol count, I believe in Wisconsin, might be 0.08, but it might be 0.1. I can't remember off the top of my head, but it's close to that. If it was 0.1, it says here that the concentration of 0.022 molar ethanol would be a 0.1% or 0.1 blood alcohol count. This individual has got a test of 0.025. So we would be over or greater than a 0.1 blood alcohol count, which means this individual is intoxicated. The chemical analysis of this sample would tell me that this individual is drunk and therefore is going to be fined, potentially would do some type of jail sentence for them being pulled over and being in this situation. So here's a great real-life scenario of how we can use titration to do something like this, which is determining a blood alcohol count of an individual. And this is using a redox titration. This same type of math is going to be applied to your lab this week, which is going to be titrating a hydrogen peroxide solution with a permanganate ion. This is going to be a redox titration where you're going to titrate the hydrogen peroxide with the purple permanganate solution. And from the results of that, once you balance the redox reaction, you will follow the same steps in order to get to the concentration of the hydrogen peroxide. So that's how we do titration problems. It's something you need to get some practice in, but once you get it, it's nice in the fact that it's very systematic. You find the moles of the one that you know both the volume and molarity of. You do the mole ratio from the balanced equation, and then you figure out the concentration or the mass by knowing the mole quantity of the substance that you analyzed. Okay? Thanks again for listening. If you have any questions, please don't be afraid to reach out. Believe it or not, this does conclude Unit 2 and all the concepts in it. The exam will be next week, and it covers 3 fundamental concepts: net ionic equations for acid bases and precipitation reactions, balancing redox reactions either in acidic and basic mediums, and lastly, to do titration problems, how to do molarity problems and with the use of titration. So continue to review these, work on these, and get prepared to take the test for next week to finish off Unit 2. Again, thanks for listening. This is not in your packet, but I just want to show you the different pieces of glassware. In a typical titration, you're going to have this piece of glassware, which is a burette. It's thinner than even a graduated cylinder, but inside of it you have markings. It starts off at 0, probably goes to like 50 milliliters. And what you'll do is you'll slowly add drips of this, of chemical, into the reagent that you're going to test. Now the substance that's in the Erlenmeyer flask is called the analyte. The analyte is the substance that we don't know the concentration for. So in this example here, I measured out 10 milliliters of HCl, hydrochloric acid, but what I don't know is its molarity. To titrate the acid, I use a base. The most common base that we use to titrate is sodium hydroxide. And let's say that it takes 15.6 mils of the sodium hydroxide to cause the reaction to reach the equivalency point. And how I know that occurs is I add an indicator to the flask. And the indicator is a chemical that will turn color. It does not affect the chemical reaction, but lets me know when the equivalence point has been achieved. The titrant is the chemical compound that goes in the burette, and that's the one that I know the concentration for. So the substance that I don't know the concentration for, I usually will put in the Erlenmeyer, and I measure out a volume of that, and that's what I titrate. The substance that's going to react with it that I know the concentration of goes in the burette, and I slowly add it until the indicator turns color. So here, the first thing we do in problems of this nature is we need to have the balanced equation. So sodium hydroxide reacts with HCl in a double placement reaction producing water and sodium chloride. I've written down the information here. There's 15.6 milliliters of sodium hydroxide, 0.1 molar sodium hydroxide, 10 milliliters of the acid, and the unknown molarity. So what we're trying to do is solve for the molarity of the HCl. Now, how do we do problems like this? The first step is you have to remember the molarity equation. The molarity equation is the moles of solute over the liters of solution. So if you look at the sodium hydroxide, the titrant, when you're done titrating, you should know both the volume and the molarity of it. And so we can figure out the moles of the solute by simply multiplying the molarity by the liters. So step 1 is to do that. 0.1 molar times 0.0156 liters. And again, you have to make sure that the milliliters has been converted to liters. Multiplying those two gives me 0.00156 moles of sodium hydroxide. This is the amount of titrant that I needed to reach the equivalency. And that's when the indicator turns color. Step 2 then, in all stoichiometry problems, is to convert the moles of the titrant to the moles of the analyte. It's a mole ratio. So that can occur in one step. And this is why we need the balanced equation. The balanced equation allows me to figure out the mole ratio of titrant to analyte. In this problem, it's 1 to 1. So there was 0.0156 moles of HCl that was in the titrant that the analyte that we analyzed. What else do I know about the HCl? Well, I also know that the 0.00156 moles was found in the original 10 milliliters. So if I divide the moles of the HCl by the original volume of the sample titrated, again, make sure that volume is in liters, that will then give me the concentration of the HCl in molarity, which for this problem is 0.156 molar sodium hydroxide. Oops, my bad, not sodium hydroxide. HCl. So the concentration of the HCl was 0.156 molar. And these are the 3 steps needed in all stoichiometry problems. Step 1, multiply the molarity times the volume of the substance. You know both of those pieces of information. Step 2, the mole ratio. And step 3, divide the moles by the volume of the sample titrated, and that will give you the concentration of it. Just like mass-to-mass problems, this is stoichiometry. It's process. Once you know the process, that's all there is to it.